Hello, welcome to your lesson on gradients and unit rates. I'm sure you've heard the word gradient or slope many times. Do you remember things about slope? Let's check. Here's a line with a certain slope. Is it positive or negative? That is a positive slope. Anytime a line is going up, and that means as the independent variable is going up, the dependent variable is also going up. That's called a positive slope. How about this one? Negative slope. Of course, it's going down. How about this one? Well, neither positive or negative. It's no slope. This one here, which one of the two lines has a larger positive slope? Hope you answered. Blue line, a steeper line indicates a bigger slope. How about here? Well, in this case, the answer is the blue line as well. The blue line has a larger negative slope. How about here? Which one has a larger slope? Hope you answered the red line. Even though the blue line has a positive slope and the red line has a negative slope, the red line's negative slope is a larger value because it's steeper. All right, for these four lines here, they are labeled 1, 2, 3, 4. Match them to the slopes we see here. And they might not be the exact numbers you see there, but which of these slopes could be the slopes of these lines? The first one is 3, 2, 1, and 4. We can see line 2 is horizontal. It has no slope, 0. We can see line 4 is negative, therefore negative slope. And the other two is about determining which one is steeper and less steep. Great job on reviewing a little bit of basics of slope. Let's talk about it some more now. So slope and gradient are the same thing. You may hear these words used interchangeably. We can begin slope with the simple words rise and run. Rise represents how much a line is moving up along the y-axis, and run represents how much we move along the x-axis. So for example, we have this black line here. We select two random points along the line, and we draw what's called a slope triangle. It tells us the slope. Here we rise 6 units and run 3 units. So the slope is 6 over 3, which of course can be reduced to 2. So let's recap some things then. The gradient of a line. The gradient of a line is a measure of the steepness of the line. The bigger the gradient, the steeper the line. It is also known as the slope. Usually the gradient or slope of the line is denoted by the letter m. Okay, we've commonly used the letter m to represent slope. So again, here we have a line segment or a portion of a line, and we want to say what is the slope. One of the easiest ways is again to draw a right triangle here, make what's called a slope triangle, and check our rise over here and our run over here. In this case, we are given two abstract points. We don't have exact locations, we just have x1, y1 representing point A and x2, y2 representing point B. So we can say the rise is y2 minus y1. That is important that you understand why that is what it is. To find this distance, like if this number here was 5 and this number was 3, we would say the rise is 2 because 5 minus 3 is 2. So we're just taking the difference between that location and this location. Here, the difference tells us how much we've risen. Likewise, along the horizontal axis, we can do x2 minus x1 to see how far this has gone. By taking this x value minus this x value, we know the distance here. That brings us to our slope formula, which is rise over run, and in that case, y2 minus y1 over x2 minus x1. How much has y changed over how much has x changed? All right, around the world, a little TOK thing for you here. You will often encounter different words for the same item, such as gradient and slope we've seen here, or trapezium and trapezoid, two different words for the same four-sided shape, or root and surd, which also mean the same thing. Sometimes more than one type of symbol might have the same meaning. To what extent does the language we use shape the way we think? All right, let's answer that. Okay, so let's recap now with slope. We have a line, we have drawn a slope triangle, we have two random locations, and again, think of it as a triangle. Here's our rise, which we call delta y, or change in y values. And here's our run, delta x, change in x values. So let's add a little bit more to our slope formula. We can say slope is change in y over change in x, which is rise over run. And again, here's that formula, how we get the rise and how we get the run. Great. So let's say these points were 2, 1 and 6, 7. Use this formula to find the slope then using these points. Well, here we go. Slope is change in y over change in x. Here's y2, 7. The y value of the second coordinate, 7 minus 1. Okay, we subtract the two y values over 6 minus 2, subtract the two x values. 7 minus 1, 6, 6 minus 2, 4. We have a slope of 6 over 4 or 3 over 2. Okay, try again. Find the gradient of this green segment given that the points are this A and B right here. All right, check your work here. 1/2 was the slope this time, a rise of 1 as a run of 2. Or, of course, we can say 2 over 4. If we look at the full slope triangle here, rise of 2 and 4 here, and we get the same answer, of course. All right, how about these two? Find the slope of both of these lines here. The first one here, you could have chosen any 2 points. I chose these 2 points. If I'm thinking of the slope triangle, I go down 2, so a rise is actually -2, and a run of 4 units. So there's my slope, -2 over 4. It's a negative slope. However, using the formula, I could have also taken those 2 coordinates and done 2 minus 4 for the y values, this 2 minus this 4 for y values, over x value of 8 minus x value of 4. So the formula produces, of course, the same slope I just saw by drawing the triangle. -2 over 4 is actually -1/2, which we see here from the formula. All right, try it for this one as well. Our slope should be 0.4. So no matter what points you chose on there, maybe you chose this one, and often it's easiest to choose points that lie right on the corners of the grid, of course, right? Because those are exact locations. Anyway, hope you got 0.4. Let's do some more. Here is a funicular railway. Maybe you've ridden one of these, perhaps in Kaunas or perhaps somewhere else in the world. These are always fun. A great way to get up hills in cities with steep hills. So funicular railway has several stations along its steep track. Station A has coordinates this and is 60 meters above station 0, which is at ground level. Station B has coordinates 230 and an unknown H value. All the coordinates are in meters. If the gradient of segment AB is 0.6, find the height of station B above the ground. All right, so let's see how we can set this up. Here's station 0, it's at a ground level. And the funicular is traveling up the hill. Here's station A, we were given the coordinates here. And here's station B, we're told it's at 230 and an unknown value here. And we are also given, it says, the gradient for segment AB. So between AB, the slope is 0.6. Maybe the slope here is different. Maybe the funicular has less of a hill and then more. We don't know, but we know this is 0.6. So why don't we use the slope formula for these 2 coordinates? And that will allow you to solve for h. So try it. Put in all these values into this formula and see what you get. Well, we set the we say slope 0.6 equals, and then using the slope formula, y value minus y value, so h minus 60. And then x value minus x value, 230 minus 30. So I put everything in that equation there, and the h is unknown, but it's the only unknown in this equation, so we can solve for it. Here simplified, we have 200 on the bottom. Then we can multiply by 200 on both sides, so 200 times 0.6 is 120, and then add 60 to get 180. So we just found out that this value is 180, and that answers the question. Station B is 180 meters, because if this is 180, and this is at 0, we are 180 meters up from the ground level. Good, simple question that has you applying your understanding of slopes. Let's try to look at another concept now. Let's talk about the steepness of a hill. How do we measure the steepness of a hill? All right, so here is a sign on the road, and we can see clearly it's showing that there's a hill coming up, and it gives a percentage here. That percentage is a way of representing hills in real life. So when we talk about how steep a hill is, we call it a gradient or a grade. Okay, we've talked about gradient for slopes, but here it's usually called a grade. So here we can see 6% grade, and here 18% grade. As that percentage increases, the steeper the hill is. And let's see how that's calculated. So here's how you do it. Slope we know is rise over run. The grade of a hill is rise over run times 100. Okay, it turns it into a percent value. So, for example, we have 4 staircases here. Please give the grade of each of these staircases. So you'll find the rise over run, which is the slope first, and then just multiply by 100. So what is the grade of staircase 1? Okay, staircase 1 has a grade of 100%, because the slope was rising 3 units, the run was 3 units as well. So slope 3 over 3 times 100 gives you 100% grade. So that gives you an idea. When we saw these grades in the last slide, not super steep. I mean, it is. 18% is quite steep, because basically what this tells us is when you have a staircase that this is 45 degrees, 45 degrees is already 100% grade. Okay, how about the next one? What's the grade of staircase 2? Well, that one has a grade of 66.6%. We had a slope of rising 2 and a run of 3, so 2/3 times 100, 66.6%. How about the next one? This one has a grade of 23.3%. Okay, a rise of 1 and a run of 3. So 1 over 3 is our slope times 100. And finally, staircase 4. Well, that one's like the first one. We have a grade of 100%. Okay, so with that in mind, I have a question for you. Is a staircase with a rise of 0 possible? Well, I guess it wouldn't really be a staircase if it has no rise and only run. It is basically the floor. It is just a flat line, a horizontal line, right? That basically means when you have a rise of 0, that means your slope is 0. It is horizontal. It's like a floor. How about this? Is a staircase with run 0 possible? Okay, that one also, I guess you could say it is, but again, not a staircase. If there is no run on your staircase and there's only rise, we're basically talking about a wall, right? It's just rising, it's not running. It's just a wall, straight up and down. Okay, how about this one here? We have, it says determine the gradient of a horizontal line. So we were just talking about a horizontal line that passes through this point. What would the slope be of a horizontal line passing through this point? Well, let's recap real quick. Horizontal lines look like this, and they always have equation y equals whatever value we have here. And vertical lines look like this, and they have whatever x equals whatever this x value is. Those are the equations of horizontal vertical lines. So can you answer A? Well, I hope for A you're thinking the slope is 0. If a line is horizontal like this one, the slope is 0. It doesn't matter they gave you a point here. The point is irrelevant. It's a horizontal line. It must have no slope. But in this case, they said, hey, we're given point D. Let's use it. Let's use the slope formula and see what happens. So we know point D, and we can actually create our own point, any other point. Like you're maybe wondering, where did this point A come from? Well, they just said, well, there must be another point. And since this is horizontal, the y value must always be 2. So see here, the y value is 2. If this is a horizontal line, any point on here will have the same y value. So they just made another point at a random location, x equals 0, and said it must have the same y value. And that makes sense. If you plug that into the slope formula, you end up getting 0, which makes sense intuitively because horizontal lines have no slope. How about B? Show that the gradient of a vertical line that passes through this point is undefined. Try the same approach as in A. Can you create another point for this vertical line? Okay, with this one, this time, if you have a vertical line, all the x values are always the same, right? Because it's always here. The y values change, but the x values are the same. So that's what they did here. They took the same point, they made up another point, and they made sure the x value is the same, 1 and 1, because it's going to be vertical that way, and made up any y value. You could choose any y value you want here, because that point can be any of the points along the line here. And then you put in the slope formula, and you notice when the x values are the same in the denominator here, when the x values are the same, you get 0. And whenever in math we divide by 0, that is called an undefined value. So that's why the gradient here is undefined. We say there's an undefined slope here. This one slope 0, this one undefined. All right, we're going to move this topic into another direction, but connected. We've talked about gradient and slope And now we're ready to talk about unit rates. Okay, so let's discuss unit rates. Unit rates are rates that show the change in the independent variable per single unit of the dependent variable. And I'll show you what this means in just a moment. But the important thing is here, per single unit. Okay, that's why it's called a unit rate. In other words, unit rates are slope reduced so that the run, the change in x value, is 1. Let's take a look. Here's an example of some real graph of time graphed versus distance. This is the independent variable, the horizontal axis, and this is the dependent variable. So here it's showing time taken to do something based on this, miles run, let's say, based on time. So let's find the rate of change. Let's find the unit rate of change. Let's begin by finding the gradient. I'm picking two random points. So I picked the starting point and this point here. All right. And I'm going to get the slope. From here to here, the rise is from 0 to 200. So this is a rise of 200. And the run is, we can see, from 0 to 5 units. So our slope, our gradient, slope or gradient is 200 over 5. Great. That's okay for a slope. But if we want the unit rate, we have to reduce this, it says, so that the dependent variable is a single unit. This bottom number, which is your x-axis, the dependent variable, is a single unit. This needs to turn to a 1. So to make this a 1, we divide both of these by 5. Or, in other words, we did 200 divided by 5. 200 by 5 is 40. So we end up with 40 over 1. 40 is the same as 40 over 1. I'm putting the 1 here so that we recognize this now as a unit rate. This means that we go 40 miles for every single unit here. And that makes sense. Look, we go 40 miles to here for 1 unit here. And then we go 1 more unit here. We went up 40 more miles to 80. We go 1 more unit. Now we're at 120. So for every unit you move on the dependent axis, you're moving up 40 units on the dependent axis. So our unit rate is 40 miles. You always say 40 of this axis, 40 miles per hour. And we can say per hour because that means per single hour, which is a unit rate. All right, let's try the same idea in these ones here. Let's do them one by one. Look at this one here. Give me the unit rate for what's been shown on this graph. Okay, in this case, I went right from beginning to end here as well. That is a rise of negative 250 because it's going down, and a run of 5. So our slope is negative 250 over 5, but reduce that down to 1 unit here. That means divide these two numbers. 250 by 5 is negative 50. So our unit rate is negative 50 miles per hour. Now, what does that mean in this situation? Well, this graphs apparently your distance from home. So as time goes, your distance from home is becoming less by 50 every hour. That means you must be traveling from somewhere far away and coming towards home, and it takes you 5 hours. Okay, next one here. They're showing water flow, maybe of 2 pipes, pipe A, pipe B. Which one, first of all, shows a faster flow of water? Well, I hope you answered A because it's the steeper slope, faster flow. So now find the water flow as a unit rate for each one, A and B. Okay, for A, you should have gone 20 gallons per minute. Again, 20 of the Y variable, 20 gallons per minute. And for the x-axis, you should have got, for the pipe B, you should have gotten 13.3 gallons per minute. If you didn't get those, double check the slope again, divide the two numbers and see if you can get those. How about this one here? We are comparing the calorie counts for butter and cream cheese. Which one will you gain more calories in? Well, the answer is butter. It has a steeper slope. So now find the unit rate. How many calories do you get per ounce of each of these? Butter, 50 calories per ounce. Cream cheese, 25 calories per ounce. These are unit rates. They are calories per single ounce. How about plant growth? Which plant is growing quicker? Plant A, clearly steeper slope. Now find the growth rate for each plant as a unit rate. 1.2 inches per week for plant A and 0.83 inches per week for plant B. Again, you found the slope and then divided the two numbers to get a unit rate. Finally, we have 2 candles. a 12-inch candle, because it starts at 12 inches, and an 8-inch candle starting at 8. And they are, as you're burning them, their height is decreasing. So what are the rates of decrease in height? Negative 2.4 inches per hour and negative 1.3 inches per hour. Hope you got those. Okay, a common place you'll see unit rates applied is in the idea of currency conversions. Let's say we have this situation. 37 euros is exchanged for 45 US dollars. If we plot this point, 37.45 is plotted right here. Here's euros, here's dollars. Okay, so this line now represents the exchange rate. How many euros we get per dollar, right? So can you find that? What is the exchange rate? How many euros per dollar? Find the gradient here. All right, so I'm going to take the gradient like that, using the full distance from 0 to the point we plotted, the 37.45 point. And our rise is 45 USD. Our run is 37 euro. Therefore, our slope is 45 over 37, and that tells us, as a unit rate, when I divide those, 1.216 over 1, which means, let's go back, 1.216 US dollars for every euro. And that makes sense. It takes more dollars to get 1 euro, and we can see that here. It took more dollars to get those 37 euros. All right, nice application of unit rates. Let's finish off with this problem here. We have Sean and Nicole walking every day, without taking breaks. Sean walks 4 kilometers per hour. Nicole walks 9 kilometers in 2 hours. So you can see here, Sean, 1 hour, 4 kilometers per hour. So we put 4 here. But Nicole, it says, walks 9 kilometers in 2 hours. So we are missing her values here. How about filling these in and these two in? What is the unit rate for Nicole? If she walks 9 in 2 hours, how much will she walk in 1 hour? Okay, now that you've filled in those values, plot them on here. One line for Sean, one for Nicole. Plot the points and then join the points and find the gradient of each line. All right, so here's what you should have in your table. Nicole's unit rate is 4.5 kilometers per hour. If you graph the two lines, you have this. And the two gradients, well, they shouldn't be a mystery because the gradients are the unit rate. So for Sean, his gradient is 4. It means he goes 4 kilometers per hour, right? That is the unit rate. And for Nicole, it should be 4.5. That is her unit rate, 4.5 kilometers every hour. Okay, this problem continues. Nicole now gives Sean a head start on Sunday, a head start of 1.5. So notice now it's 5.5 in 1 hour for him because he's still walking 4 kilometers an hour, but he had a head start of 1.5 kilometers. So he made it 5.5 in that first hour. But after that, he continues to go at 4 kilometers per hour. And for her, the same rate as before. So now fill the tables and graph those. And the question is, how many hours will it take Nicole to catch up with Sean? Okay, so here's the tables. And in the tables, we can see at hour 3, they are at the same place. They have gone 13.5 kilometers. And that is confirmed on the graph. We have the two lines, and at hour 3, the two lines intersect. That's when they've gone the same amount. All right, so that's where we're going to end it today. I hope you have a strong understanding of unit rates and their connection to slopes and gradients. That was the goal of this lesson. We will see you soon.